Hi everybody, welcome to my video on how to identify if a molecule is polar or nonpolar. And here I'm going to show a picture of water. This seems to be a theme for all of my talks. And one of the most important polar molecules in all of chemistry is water, and we'll talk today a little bit how we take what we know about Lewis structures and three-dimensional shape and VSEPR and identify whether a molecule is polar or nonpolar. And I will say polarity is one of the most important skills to be able to recognize polarity in all general chemistry, organic chemistry, and biochemistry because it has such a large impact on the properties of that molecule from both physical properties, boiling point, melting point, as well as chemical properties and reactivity. So let's take a look at how we're going to go about it. So in this video, we're really going to just do a lot of examples. But first I want to set up the framework of the kind of the thought process that we go through in order to assess whether a molecule is polar or nonpolar. So the first step is going to always be to draw the Lewis structure. Because the Lewis structure shows us connectivity, so how atoms are connected and what atoms are connected to other atoms. So we have to know the connectivity before we can assess polarity. And then secondly, we need to use VSEPR, valence shell electron pair repulsion analysis, to determine the 3D determine 3D geometry. And I'll just write molecular shape here, because we're going to look and do some vector analysis and identify how these molecules will pull in 3D. Third, we're going to draw in dipoles for each bond. So we're going to draw dipoles and indicate bonds that are polar covalent bonds. And we're going to do this with electronegativity differences. As a reminder, the difference in electronegativity, delta En, electronegativity just for En, between greater than 0.4 and up to 1.8 will signify a polar covalent bond using the Pauling electronegativity values. And you can have that table in front of you and do these calculations, but what I'm going to ask you to do is really start to look for those highly electronegative elements on the periodic table. These are the guys that all sit up, in the upper right-hand corner of the periodic table over here. So these are my high electronegativity elements, and this is basically going to be, looking for oxygen, nitrogen, fluorine, chlorine in some cases, bromine. These guys, if you see these in a molecule, even back before you even draw the Lewis structure, you need to be thinking that this could possibly be a polar molecule. Not always, and we'll show some examples of that, but this should really clue you into that you really need to think about the polarity of the molecule when you see these atoms in there. And then lastly, we need to determine the net dipole. Which is a series of vector addition. But again, instead of like going into a lot of detail and doing the math behind adding vectors, we're going to look for points of asymmetry. And I'm going to show you kind of how to do that, thinking about molecules as mini tug-of-wars. So what we're really doing is adding vectors for dipoles. All right, so let's get into some examples, because the real way to understand polarity is just to do a whole bunch of these as examples. The first example that I'm going to do is my favorite, and that is water. So we start out with the molecular formula for water. We have to draw the Lewis structure first. And really, at this point, you really should just know water is a bent geometry from Vesper. We have 4 electron groups, 2 bonds, 2 lone pairs. That forms tetrahedron electronic geometry, or a bent molecular shape. And it's got a bond angle of around 105 degrees. So here I have my Lewis structure and my Vesper analysis. I'm just kind of sketching this out as bent. And we can then start to look at drawing in these dipoles, so assigning electronegativities. And we can immediately see we have one of those big boys in electronegativity, and that is oxygen. And oxygen is highly electronegative atom, and we can calculate the difference here between oxygen and hydrogen, but again, this is one of these things that you really should just know. This oxygen-hydrogen bond is going to be polar. So oxygen, highly electronegative, that means the hydrogen is going to be slightly positive, because all that electron density is getting pulled toward that oxygen atom. And then we can draw in our dipole, which is that arrow that points toward the electronegative atom. And we have something like this. So we know we have a molecule that has polar bonds, but we're not quite done yet. We have to think about how these vectors, these dipoles, add together. And if they have a net resultant vector, then it's going to be polar. If the vectors cancel out, then it will be nonpolar. And that's this idea of asymmetry. Sometimes this asymmetry is a little hard to see, because we know tetrahedron is an asymmetric geometry, but these lone pairs don't really pull on the molecules, so we only have 2 covalent bonds, and we don't really have anything that's counteracting that. But the easier way to think about this is really as a tug-of-war. So let's look at a tug-of-war here. And we have oxygen here. And then we have our hydrogen. So that's oxygen up here. And imagine that they are connected via ropes. So we're got a rope here and a rope here. And oxygen, because it's electronegative, is really pulling on that rope. So let's think about what happens to my oxygen, which is the central atom here, as he is pulling on these two hydrogen atoms. If we think this molecule will move as a whole, then it will be polar. If the molecule does not move, then it's nonpolar. So in this case, if you have these two guys here, or girls, people, at an angle, and you're pulling on it, you're going to have a net movement of this whole molecule up. And so I have a net dipole toward the oxygen, which is going to result in a polar molecule, where I have this negative end of the molecule toward the oxygen and the positive end of the molecule down by the hydrogens. So let's look at a second example. Carbon dioxide. Again, I have oxygens at play here, so I really need to analyze if this could be polar or not. So we can draw our Lewis structure for carbon monoxide. We know that carbon is bonded to the two oxygen atoms with double bonds. Again, we know oxygen is highly electronegative, and then carbon is left as positive, because that electron density, like oxygen really likes those electrons, so it's pulling that electron density toward that oxygen, and same with this one. And then this is going to be two electron groups, and so this is linear at 180-degree angles. So again, thinking of my tug-of-war, I can go ahead and draw my dipoles in. I have a dipole pointing this way toward the oxygen, and I have another one pointing from the carbon to the oxygen. And we can think about the tug-of-war again between my three atoms. And he is connected with ropes. And in this case, this oxygen over here is pulling that way. And this oxygen over here is pulling that way on that carbon. So what happens to, again, this central atom, which now in this case is carbon? This carbon is going to be counterbalanced, right? Because this oxygen is pulling, and they're pulling at the same strength because it's the same bond on both sides. And so this is also going to be canceled out in this case. And so these two vectors, these two dipoles, will cancel each other out, and I will have a non-polar molecule. This molecule is going to be considered nonpolar because the dipoles cancel. And if I drew it in terms of vector addition, I would have one vector with the same magnitude going in the opposite direction, so there's no net dipole. So even though I have polar bonds, does not always mean that I will have a polar molecule. So we have to look at both the geometry and the atoms involved to determine the polarity. So I want to do a few more examples with some different electronic geometries associated with them. So one I want to look at is SO3, sulfur trioxide. And I'm going fast on drawing these Lewis structures. So if you need to go back and practice the Lewis structures, go back to some of the earlier videos in the series. Because if you can't draw the Lewis structure and determine the VSEPR, then you're not going to be able to assess polarity. So this is SO3. It's got 3 electron groups, so it's trigonal planar with a 120-degree angle. So trigonal planar. When I go in to put the dipoles, again, I see that these oxygens are out there, and so they're very electronegative, which means my central atom, again, is going to be positive. And it's always a good idea, especially when you're just starting with this, you can check your Pauling values and check the differences to make sure it does fit indeed into that polar bond category. But you will build up basically some chemistry muscle memory to recognize when you have these polar bonds. So I'm drawing my dipoles here, and I'm going to show them over here. And we can see, again, thinking about this as a tug-of-war on that central atom, I have 2 pulling this way and 1 pulling down. And just visualizing it from the standpoint of a person pulling on those ropes, you probably innately recognize that that center is not going to move, and so there's no net dipole here. Might not be as obvious to see this in terms of vector addition. So in terms of vector addition, I have 2 going up this way in my y component, and my x components, they cancel because I have this side canceling out that side. And then these 2 ups end up being exactly the 1 going down. So these are half the distance as the 1 going down in terms of height. So it does have no net dipole. And this is a symmetric geometry. So this is a non-polar molecule. But always think about it as kind of these ropes pulling just at the corners of an equilateral triangle. But be mindful, I'm going to show another trigonal planar example with formaldehyde, which has a Lewis structure like this. This is also trigonal planar. 3 electron groups. And I can draw in my dipoles. But carbon-hydrogen here, this carbon-hydrogen is not a polar bond. This is a non-polar bond. it's another one that you really should just know that this carbon hydrogen is nonpolar. The difference in electronegativity is 0.4. So there is no dipole on this carbon hydrogen bond. So I only have the one dipole between carbon and oxygen here. So this molecule has a net dipole toward that oxygen. Nothing to cancel it out because I don't have polar bonds between carbon and hydrogen. And so this is a polar molecule. So not everything that's trigonoplanar is nonpolar. So be careful. Just really think about, again, looking at these as those rope diagrams. I will say that if you have four of the same atom all attached, you can look at some of these geometries as symmetric or not. But it's better just to think about what's pulling, what's polar bonds. If we look at something like CCl4 and draw the geometry here. This is tetrahedral, which makes my little spaceship-like friend here. And chlorine, carbon. So my chlorines are electronegative relative to carbon, and we get the 4 dipoles. Leaving that central carbon partially positive. But because this geometry, the tetrahedral geometry, which I sketched out here, it's very similar to the idea with my trigonoplanar that the one up is 3 times the height as it is off the plane. So the one up cancels all 3 of the downward components. And here, because I'm in 3D, so my Z component will just say Z. So that's X, Y, Z. My Z component is canceled out, and my Y and my X component will be canceled out. And so this is a symmetric geometry where all these dipoles will cancel out, and it is non-polar. I want to do one last example just because, again, it's my favorite. We'll look at SF4. SF4. Fluorine is hanging around. It's almost always a polar bond when I have fluorine, unless it's attached to another fluorine. And we can look at fluorine. Here, this is 5 electron groups. It goes into the seesaw geometry. So if I sketch that out, looks like a little seesaw with my little lone pair sitting out there. Those fluorines are very electronegative. And my sulfur is positive. So if we sketch out our dipoles on this, and just because it's a little busy over there, I have 2 pointing down. So these coming across will cancel each other out. This pulls the same. That's going to cancel each other out. But there is nothing to cancel out my two downward floorings. And so I have a net dipole for this. Downward. Because I need to have something to counteract these guys pulling. Again, if you thought of this as ropes positioned at these 4 points, it would be pretty obvious to realize that it's going to pull that central atom down. So I hope this helps with identifying these polar molecules. Again, it's very important to be able to do this as you go through your chemistry courses, and very important in terms of pharmacology and in general understanding chemical behavior. Thank you. Have a great day.